Hello everyone, this is Sherry Sahebi and it is data mining class. So today we are going to talk about singular value decomposition or SVD. We know that in PCA or principal component analysis, we do have a covariance matrix sigma achieved from our data, which is d by d, and to reduce the dimensionality of the data, we get eventually to this equation that sigma ui is equal to lambda I ui for I that is between 1 and D. Now, if the rank of our matrix is lower, the lambda i's are going to be 0 in the latest ones. And because our sigma covariance matrix is positive semi-definite, we know that we can arrange our lambda i's from largest to smallest, like this. And we know that all of our eigenvalues or lambda i's are going to be larger than or equal to 0. So if we put together all these different eigenvectors that we can achieve like that and build a matrix U like this, so we can have a matrix U with UI, U1, U2, etc. until UD, like this, then it's a D by D matrix, right? Then we can also put together all of our lambda i's or eigenvalues like this, lambda 1, lambda 2, etc. until lambda D zeros all over on non-diagonal elements. So this is our lambda matrix. Then we can rewrite this formula above, which is the eigenvector decomposition, like this. We have sigma, our matrix sigma, multiplied by matrix U is equal to our diagonal matrix lambda multiplied by matrix U again. So U actually comes here, matrix U and diagonal lambda. So what we can do is that we can multiply both sides of this equation with inverse of matrix U. So if I multiply both sides to inverse of U, what I get is sigma U inverse of U is equal to U lambda inverse of U. Now this is I, so on the left hand side only sigma remains, and on the right hand side, because our UI's are orthonormal to each other, we know that U minus 1 or inverse of matrix U is equal to U transpose, right? So basically on the right hand side, we will have U lambda U transpose. Okay, so this is what we get in PCA, and basically what we are seeing is that we can rewrite our covariance matrix, sigma, which is D by D matrix, as a multiplication of 3 other matrices, U, lambda, and U transpose. And U and U transpose are orthogonal matrices, so their columns are all U's that are perpendicular to each other, and then lambda is a diagonal matrix. So we can look at this decomposition in another way also. So this is called a decomposition of our sigma matrix. Whenever we are rewriting our matrix as a multiplication of other matrices, we are decomposing that matrix. So what are we doing here? We are actually writing sigma like this. We have all the UIs like here, U1, U2, UD, multiplied by lambda 1, lambda 2, etc., lambda D, multiplied by now U transpose is U1, U2, UD, right? So I can rewrite this multiplication in terms of vectors now. I can say that this sigma is equal to U1 lambda 1 U1 transpose, so vector U1 plus vector U2 lambda 2 U2 transpose plus vector UD lambda D UD transpose. Because lambda i's are scalars, what I can say is that this is equal to sigma over I, lambda I, UI, vector UI, and vector UI transpose, right? Okay, so what are these UI transpose? We know that each of our UIs are basically D by D, right? D by 1. So here we have a D by 1 matrix or vector, and UI transpose is a 1 by D vector. So their multiplication is going to be a D by D matrix that has rank 1, right? So when a matrix is achieved by multiplying to vectors only, like a vector and its transpose here, that matrix has rank 1. Okay? So in other words, what we are having is that we can rewrite our covariance matrix sigma as a summation, weighted summation of D rank 1 matrices. Why weighted? Because they are weighted by lambda i's. And then we have D rank 1 matrices that are achieved using UI transpose. Okay, so covariance matrix is a combination of rank 1, D rank 1 matrices that we have. Now, what we see in this decomposition is that it is applied on a covariance matrix that has that is D by D. So the number of rows and columns are the same with each other. Now, there is another very famous decomposition that can be applied on any size matrices. So we can basically directly apply SVD or singular value decomposition, this decomposition that we are going to talk about, to our data matrix. So how is it defined? Singular value decomposition, or SVD. In SVD, given that we have any matrix that has real values, so it's m by n, it doesn't need to be n by n or d by d or anything like that, we can rewrite this matrix as multiplication of 3 other matrices. U, or the left singular vector, it's on the left-hand side, right, of this these 3 matrices. It is an M by R matrix. Sigma, which is in the middle, it is a diagonal matrix that is R by R, and V transpose, V is, we call that right singular vector. It is an N by R matrix that when we transpose, it's going to be R by N, and then it can be multiplied by sigma. R is usually smaller than M and N. Okay. So we can have different interpretation for SVD. For example, in one of the interpretations, we can assume that our A data matrix is representing M documents and N words or terms. So what do we mean by this? You have seen something similar in your homework. What we mean is that, suppose that I have multiple chapters of a book. Each chapter is one document. And then in each chapter, I'm going to see some words, right? So for example, in chapter 1, I see words like numeric or feature. And in chapter 2, I see words like PCA and feature. So what I can say is that chapter 1 has numeric and feature in it. It doesn't have PCA, but chapter 2 has only feature and PCA in it. Something like that, okay? And then after I decompose A into these 3 other matrices, I can interpret U, my left singular vector matrix, as a relationship between the documents or chapters and the concepts that are presented to them, in them. Note that the concepts are not given to us before. They are some latent concepts. The singular values can represent the importance of our concepts, and the right singular vectors can represent how much each concept, how much each word is important in each of the concepts. So we are going to see something like that later on also. So don't worry if you didn't understand this fully. So let's look at SVD and see how it is similar to PCA somehow. Does it remind us to PCA or not? So you remember that in PCA, what we had was our matrix sigma could be decomposed into U lambda U transpose, right? Here we have our matrix A being decomposed into U sigma V transpose. See? So our right-hand side matrices are different from each other. But similar to PCA, that we could write sigma as a summation of rank 1 matrices, we can also rewrite SVD as a summation of rank 1 matrices. How? We can say that we can rewrite this as a summation of these sigmas are basically these singular values, and then we have product of UIs, vector UIs, and vector VI transposes. Okay, so in this picture, for example, we have an M by NA, and then we can suppose that we have two singular values. We can rewrite that as a M by R or 2 matrix U, an R by R sigma, and an R by N V transpose. Okay, so this column of U, if we take the product of it with this row of V, we are going to get a rank 1 matrix that weighted by this sigma I is going to give us some portion of A. So like this. So we have A. It's basically a multiplication of U1 product with the first row of V and multiplied by sigma plus another one similar to that. So what are SVD properties? Why do we care about SVD so much? It's because it has very nice characteristics that are useful for us. First property is that always we can decompose any real matrix into 3 matrices, U sigma V transpose. And then these matrices, they do have their own properties. First of all, there is a unique SVD decomposition. So if I give you one real matrix, it doesn't matter how many times you run SVD on top of it or you calculate SVD for it, you always are going to get the same results. With this constraint that U and V are column orthonormal matrices, meaning that similar to what we have seen in PCA, U transpose U is equal to I, diagonal matrix, ones on the diagonal, and V transpose V is also equal to the identity matrix I. So the columns of these matrices are orthogonal unit vectors. And also sigma is a diagonal matrix that its entries on the diagonal are positive and can be sorted from the largest to the smallest, similar to what we have seen in PCA. So the sigma, the entries on the diagonal of sigma, we call them singular values. And the columns of U and V are singular vectors. So let's see an example of interpretation of SVD. Suppose that our data matrix is this data matrix, and it shows how much users like movies. So for example, each row, it shows the ratings of one user on all the movies that we have. So for example, the first user likes Matrix, Alien, and Serenity with 1 star and didn't like Casablanca and Amelie. And then our last user didn't like Matrix or Serenity and then gave 1 star to Alien, 2 stars to Casablanca and Amelie. Okay? And then if we look at each column, we see how all of our users have rated one movie. Okay, now I can decompose this data matrix into 3 other matrices with SVD to use sigma V transpose. And let's see what happens then. these are the values that I get for U, sigma, and V transpose. So first of all, looking at this whole matrix, again, similar to PCA, we can see some patterns in our data. So we can see that some of our users, they are mostly sci-fi fans, right? They rated Matrix, Alien, Serenity. And some others are mostly romance fans. They rated Amelie and Casablanca. They also sometimes like sci-fi or like that. So we are already seeing a kind of pattern in our data. Now, if we look at the decompositions, we see some meaning or pattern in the decomposition also. The first thing that we see is that we can look at each of these lower dimensions. This is a user by R matrix, right? To be representative of a concept in our data. So, for example, the first column or the first lower dimensional vector or singular vector, it can be representative of sci-fi concept. Why? See, the values are larger for users who like sci-fi in this column and smaller for the users who liked romance. But then, if we look at the second and third columns, we can see that it's the other way around. The absolute values, so the magnitude of values in column 2 and 3 are larger for the users who like romance movies. So maybe we can say that these two columns are mostly about romance concepts. Okay? So basically our matrix U is representative of a similarity between users and the concepts that we can find in the movies. Again, the concepts are hidden. No one has told us that this is sci-fi, this is romance, but we are interpreting them as being sci-fi or romance. So this matrix U that has user 1, user 2 until user M in it, each element shows how much one user is interested in one concept in it. Okay? Now, how about the sigma matrix? The sigma matrix can show the strength of a concept in our data set. So, for example, we can see that the concept, the first concept that was related to sci-fi has a strength of 12.4 in our data. That can explain the variability in our data. How about matrix V? Now in my matrix V, we can see that each row is a concept and each column is associated with a movie, right? Because V transpose is R by N, so N is coming from the movies and R is coming from the concepts that we have. So what it shows is a similarity. It can be interpreted as a similarity between movies to concepts. In other words, it is telling us how much each concept is represented in each movie. So for example, if you look at Matrix, we can see that it's mostly sci-fi. And it does have a little bit of romance in it, but not much. But then if we look at Alien, we can see that in addition to sci-fi, it does have some romance in it. And that is because we can see that Alien has been rated by both users that like sci-fi and like romance movies, right? So this is our first interpretation of SVD. What we are thinking of is that we have movies and users. Our data set is having movies and users, and there are some concepts that are hidden in our data set. And by doing a decomposition like SVD, we are figuring out what user to concept similarity is, what movie to concept similarity is, and what is the strength of each concept in our data. So if you go back to the document, word, and concept interpretation that we had at the beginning of this session, you would get that interpretation too. It's similar to movie user concept interpretation. But there is another interpretation to our SVD also, and that is the dimensionality reduction interpretation. What is that? We said that in dimensionality reduction, what we want to do is to reduce our the dimensions in which we are representing the data, so the features, and that way it will be easier to work with our data. But also the dimensionality reduction would summarize our data, so it will be easier to represent our data in a summarized way, and it will help us to find patterns in our data. So let's look at that perspective of SVD. Suppose that we have two movies in our data, and each data point is basically one user in this two movie space. So we have movie 1 rating and movie 2 rating, and for each user we can say what is the rating of that user in movie 1 and in movie 2. Now think that instead of using both of these axes to represent each of the points, we want to only use one coordinate or one axis. Reduce the dimensionality, right? So how are we going to choose that axis? We want to choose an axis that when we reconstruct, so we choose a direction, we project our data points into that direction, right? And our goal is that whenever I look at this smaller dimensional representation, and whenever I get back to the original representation using the smaller representation, I don't lose that much of information. So basically, we want to be able to reconstruct our data in the original space, both movie ratings, without losing lots of information. Or in other words, minimizing the reconstruction error. So an example would be like this. In our movie concept matrix and user to concept matrix, the direction can be the first right singular vector that we have. So the first right singular vector, which is associated with the largest singular value that we have, can be a direction that we project our data on it. And then this singular value is going to be a representative of our variance or spread of our data on this direction, the direction of first singular vector. And then to find the coordinates excuse me, to find the coordinates in the projection axis, we can look at multiplication of u and sigma. And basically, this gives us the projection of our users into this direction, which is our sci-fi axis, right? So multiplication of u and sigma are going to be our projections into sci-fi axis, which is basically how much similar each user is to the sci-fi axis multiplied by the variance or importance of the sci-fi axis in our data. Okay. So, okay, we said that this is going to cause dimensionality reduction, but we didn't say how this is going to be done, because we are seeing m here and n here. This is m by r, this is r by r, this is r by n. So I'm not sure, is one single m by n matrix larger in terms of the space that it is taking from us, or three matrices, that one is m by r, the other is r by r, and the third one is r by n, right? So here in the original matrix, I only need m by n real numbers to be able to represent it. But in the decomposed one, I need m by r plus r by r plus r by n, which is r multiplied by m plus n plus r, right? Do I actually summarize my data when I'm representing it like that? Well, in most cases, yes, because r is usually selected to be way smaller than m and n. But also there's another way to reduce the dimensionality of our data, and that is by looking at this singular values. So we said the singular values are the importance of each concept in our data set. So also they are ordered from the largest to smallest. So sometimes when we want to make our data even smaller, we can just remove or drop the singular values that are too small or that are smallest to 0. Okay, so I remove this singular value here, and if I set this one to 0, then I can say that my original matrix is not equal to these multiplications anymore. It is estimated by these multiplications, right? Because we are losing some information here by setting 1.3 to 0. But when I set this guy to 0, in the multiplications, it is as if I am removing this vector, like this column and this row. So it doesn't matter if I keep the numbers in these two or I just set them to 0. The multiplication is going to stay the same. You can try and see it actually. So basically, it means that when I drop this guy, I'm dropping a row and a column also. So I'm going from r to r minus 1 if I'm dropping one singular value, right? If I drop r prime singular values, I go from r to r minus r prime. So what remains is that basically I'm representing my original m by n matrix with r prime, r minus r prime, m plus n plus r minus r prime matrix. Okay? So basically we are reducing concept dimensions to represent our data. Again, what we get out of these multiplications are not going to be exactly the same as our original matrix, right? But they are going to be close. Now, how close? We can actually calculate that. How? We can multiply these three matrices and see what matrix we are going to achieve. Now, if I multiply these three matrices, my results are going to look like this. And you can see that the numbers in this matrix are close to the numbers in the original matrix. They are not exactly the same, but they are close to each other. Now, to see how close, what I can do is that I can just take the differences between every two elements in the two matrices and square them, because the distance is important for us, right? We don't want them to cancel out each other. So square them and sum over them and take the square root of that. And that is called the Frobenius norm of this subtraction matrix. The whole goal of dimensionality reduction in SVD is that this difference, or in other words, the error that we get by removing one or multiple of singular values, is as small as possible. Okay. Now, because we are removing the smallest singular values, these are the ones that are having the least importance in our data. And it can be shown that SVD is actually the best low-rank approximation possible to our original matrix. Now, talking about rank, you remember here, let's go, yes. So you remember here that we were summing over sigma I ui vi's, and I was from 1 to r, right? R in SVD is equal to the rank of matrix A. That's why it is less than or equal to M and N. So, for example, if we have a 1000 by 100 matrix, but the rank of this matrix is 2 or 3, so suppose that is 3, then we can represent this matrix using a 1000 by 3 plus 3 by 3 plus 3 by 100 matrices. Okay. Now, if we want to even go into lower dimensions than 3, so originally SVD has the rank, right, which is 3 dimensions. We can go even lower. We can go from rank 3 to 2. And because we are removing the least important singular value and singular vectors from our decomposition, then this rank 2 approximation is the best rank 2 approximation that we can get from A, meaning that when we build this matrix B out of multiplication of like U that only has 2 columns and V that only has 2 rows and sigma that is 2 by 2, B is going to have rank 2, right? And this B is better than any other rank 2 matrix in terms of closeness to A. So calculating SVD is a little bit complex. It's usually an order of n multiplied by m squared or n squared multiplied by m, depending on which side is larger. But if we just want the singular values, or if you're only looking for the first k singular values, or if the matrix doesn't have all of its elements to be non-zero, so it is sparse, then it will have less computational complexity. So there are algorithms that are approximates and they are less computationally intensive. Now, SVD is implemented in lots of linear algebra packages in all different kinds of programming languages, so you can just use that. Okay, now that we have learned about different interpretations of SVD, the question is this. Okay, how can I use that to query my data? So for example, consider the movie user matrices and its SVD decomposition. Suppose that we would like to find users that like the movie matrix. Okay, how can we answer that using SVD decomposition? So what we are going to do, because after we have done SVD, we are in this space, right? We have these matrices. We are not working with the original matrix anymore. So first thing that we have to do is that we have to translate our query, the query is users that like matrix, into this new concept space, right? So that we can basically represent our query similar to the matrices U, V, and sigma. Okay, so the first thing that we can do is that we can say, who are the users that like matrix? A user that likes matrix, their row vector looks like this, right? So this user has definitely liked matrix with a large star, like 5 stars. And then for other movies, well, we don't know if they like it or not, so we leave it at 0. This is our original query. Now we have to project it into our concept space because we want to be able to compare it with user concept and user concept and concept movie matrices. So to do this projection, what we can do is that basically we can take the inner product with each of the concepts that we have. What are the concepts that we have? They are represented in our V matrix, right? So we multiply our query with the V matrix, which is movie to concept similarities. So here I have movies. Here I have similarity between movies and concepts. So as a result, I will get concepts here, right? Importance of each of the concepts here. So after I did that, I will get what's the importance of such a user in the sci-fi concept, or the similarity of such a user to the sci-fi concept and to the romance concepts. Okay, now that I have done that, well, I know that the users who like movie matrix are going to look like this. They are similar to this kind of concept representation. So I can actually compare all my user concept, all the rows or users in the user concept matrix to this vector and see which ones are like that. Now, if I want to do that, if a user has actually weighted matrix high and it looks exactly like this, so I would say, yes, this user likes the movie Matrix. But then there may be another user like this guy who seems to like the sci-fi movies, but we don't know about this person's interest in the Matrix movie. See, so Matrix is 0, Alien and Serenity are 5, so it seems to us that this person likes sci-fi. Now, if I want to compare this person with our query that we had originally, our query was like this, it was 50000. If I want to compare this with this, using the dot product between the two, I will see that basically the dot product between these two is 0, these two 0, 0. So the similarity between these two people are 0. But then I know and you know that this person and this person both like sci-fi movies. Can SVD help us in that? Yes, it does. So, for example, if we map this user from the original movie space into the concept space, again, by multiplying the user to the movie to concept similarities V, we will get to this concept vector, 5.2 and 0.4. So our matrix query in the concept space looked like this vector, and the user that we are looking at that didn't rate matrix but rated Alien and Serenity looks like this in the sci-fi concept and romance concept. Now if we calculate the similarity between these two vectors or the dot product between these two, the similarity is not going to be 0 and it's going to be more than 0. So you see, we could capture the similarity between these two users in the concept space, but we couldn't actually do that in the original movie space. So using this, that the similarity in the concept space is non-zero, we can actually say that, yes, this person probably likes Matrix too. All right, so what we have learned is singular value decomposition. It is similar to PCA in terms of being decomposing matrices into lower dimensional matrices, one of them diagonal, the others orthonormal. But it is more general than PCA because it can factorize any matrix. And it can basically factorize any matrix that is our data matrix into left singular vector matrix, the singular value diagonal matrix, and right singular vector matrix. We have seen that originally if we do SVD on top of our data matrix, we are going to have matrices that are M by R by R, and R by N, that R is the rank of our data matrix. And we can rewrite our data matrix like this. But also, we have seen that if you want to have a more compact representation, we can drop the least important singular values that are smallest and have an approximation of our original data. And we can see how good our approximation is by calculating the Frobenius norm over the difference between the original data matrix and the reconstructed one from SVD. Now, how can we connect between SVD and PCA? Let's look at this in more details. So we said that our D matrix, data matrix D, can be rewritten as, let's use this notation here so that not to confuse the two sigmas with each other, as L delta R transpose, right? Which is delta is the diagonal matrix, and L is the left singular vectors, and R is the right singular vectors. Now, PCA, if you remember, it was on the covariance matrix, right? So the covariance matrix is kind of similar to D transpose D, right? We know that if our data is centered, so if the mean of our data is 0, then D transpose D is equal to N multiplied by the covariance matrix in the data, right? So D is centered. So we know this. Now, if I rewrite D transpose D according to its singular value decomposition, what I get is I am having L delta R transpose multiplied by L delta R transpose equals to N sigma. Okay, basically it means that R delta L transpose, delta transpose is equal to delta because it's a diagonal matrix. L delta R transpose is equal to N sigma. Now, L transpose L is I because we have orthonormal vectors, right? So basically what we have, also delta multiplied by delta transpose, or delta multiplied by delta, is also a diagonal matrix that on the diagonal the values are going to be equal to delta squared, right? So we have R delta squared R transpose is equal to N sigma. Oh, this looks a little bit familiar to me, right? So if I move N to the other side, I can say R delta squared over N R transpose is equal to sigma. From PCA, you remember that sigma, we could rewrite sigma with its PCA as U and lambda U transpose, right? So these two equations are very similar to each other. It seems to us, so what we can conclude is this: R, which are right singular vectors of our data matrix, are equal to U, which are eigenvectors of our covariance matrix. And also, at the same time, it seems that lambdas, which were our eigenvalues of the covariance matrix, are equal to the square of our singular values divided by n number of data points. So we have n lambdas are equal to, it was equal to the variance of each attribute, right? So lambda i's are the variance divided by n for all of our attributes. So this is the relation that we get if we look at D transpose D, which is similar to our covariance matrix in the data. Now, if we look at, what if we look at DD transpose? If we look at DD transpose, we are going to conclude something about the left singular values, left singular vectors, sorry. And so what you can do is that you can try that at home and see what you will get. So that is it for our singular value